All right, everybody, welcome back to yet another installment of the Damage Control Assistant Senior Enlisted Curriculum. I'm Lieutenant Timothy Mueller. I'm going to be the instructor for Chapter 2, Lesson 4, where I'm going to talk about how to calculate the kg when you have a weight addition or removal on a vessel. Now, similar with what we had with a weight shift, we're going to look at two different situations mathematically. We're going to try and find some sort of a relationship between the two and extract a formula on how to find either the coordinate or the change in a coordinate of the center of gravity. So here we're going to have a system of two masses, then we're going to add a third onto it. So the original state is M1R1, the total system, equals the moment of this first item plus the moment of the second item. Now in the second situation, we're going to add a third item, M3R3, but we know that our total mass, or the system's total mass and the system's overall center of gravity coordinate are going to change. So it's going to be M2 and R2 here. Okay? Now we have to start linking some things that we already know. We know that M2 equals M1 plus some delta M, but we know this delta M is going to be M3, so it's M1 plus M3. And we also know, looking at equation 1, we can substitute all of this in for this. So we can just take the total system that we had before and just substitute it in for everything that it equates to, because the big system here equals the sum of 1 and 2. We see the sum of 1 and 2 here, so we just substitute there. Now, if we just work everything out, we just look at equation 2, we're not subtracting equations from anything this time. We look at M2R2, we're just looking at this equation here, equals M1R1, which is just this summation here, plus M3R3. Now we want to find out what the coordinate of our center of gravity is, so we just have to isolate R2. By isolating R2, we just divide both sides by this M2, this big M2, which is going to be the mass of our final system, and bring it over here. So we have R2 equals M1R1, that's going to be the original system, plus M3R3, the thing that we added, divided by M2, which is also M1 plus M3. Now, if we put that into ship stability terms, we have kg1, our new kg, equals the original kg times the original displacement, because this was our original system. Here's our original displacement, our original kg, plus W that we added times this lowercase kg, which is going to be the center of gravity of that specific item. Here we have M3 and R3, and it's divided by the final displacement, which is just M1, the total mass of the system before, plus what we added. Now you can see, if you take this, if you're subtracting that weight, nothing changes. You can just say, there. So it's plus or minus whatever that item is. If you have any more items on here, if you do the same exact setup, you can just add or subtract those additional items onto here. So all you have to do is just append another, W2 little kg2 minus W3 kg3, and then nothing changes. However, you have to remember that your displacement is going to be your original displacement plus all those additional items, and you're going to get the exact same result, which is going to be your new kg. If the equation for finding the center of gravity of a system came pretty naturally to you, then you probably found that equation to be pretty intuitive. Now let's go into an example problem using this equation. Here we're going to find kg1. We have an original vessel displacing 13 long tons, and it has an original kg of 2 feet. So we're talking about a pretty small vessel. We're adding 1 long ton, and it's going to have a kg of 3 feet. So we have one piece with a mass of a weight of 13 long tons at 2 feet. We're adding something up higher, so we're expecting an answer that's going to be higher than 2. Okay. Now, plugging everything into the formula, we have original displacement 13 long tons at its original kg 2. Since we're adding the weight, we're we're adding the moment from that weight. So we have 1, which is the weight, the long ton, times 3, which is the location that we're adding that weight to. If we were removing this weight, we would have this as a minus sign. However, since we're adding it, it's a plus sign. No matter where it is on the, if it's above or below the center of gravity, we're still adding the weight, so it would have to be an addition. Then we divide it by the total mass of the final system, which is going to be 13 long tons plus 1 long ton. It's going to give us 29 divided by 14, or 2.07 feet. Once again, you're going to have answers right in this range. In the last video, we saw something that gave us the movement of G. Here, remember, this is the location of G from the keel. So we're getting a little bit more information in this one. If you were asked the question, how far does the center of gravity move? You would just take this new kg, kg1, and you would subtract from it kg0 or kg0, which is 2 feet. And you would get the answer that the center of gravity moved up 7/100ths of a foot. So far in this chapter, we've talked about the reference points on a ship. We've talked about how to find kg using moments as a more graphical representation. Then we dug a little bit more into the weeds and we found out how to calculate the movement of center of gravity in a weight shift. Then we found how to find the new kg when we're talking about weight removals and weight additions. In the next video, I'm going to introduce rolling period, and that's something that's directly correlated with the metacentric height. You saw how the metacentric height changes generically with the metacenter and the center of gravity moving with each other. However, this is a tool that you can use when you're approaching a vessel. You can get a quick measurement of how quickly the ship is rolling from side to side, and you can make a pretty reasonable approximation as to their metacentric height and how stable they are. Until then, I'm Lieutenant Timothy Mueller, and I hope you have a great day.